We asked how much does each observation, so each individual observation, vary around its own group mean. And then again, we have, in this case example where you see the pictures, how many of those do we have? We have 3 sets of sums of squares. We're going to get the sums of squares for this one, the sums of squares for this one, and the sums of squares for this one. Then we divide it by degrees of freedom. We're going to add those all together. We're going to pool them. We're going to divide that whole thing by degrees of freedom, and we're going to get our variance. That's our error variance. Now, is f a function of variance and sample size? If the degrees of freedom, think about it conceptually, degrees of freedom always starts with the number of pieces of information that we have. How many pieces of information went into this? 3. That's it. How many pieces of information went into this? Conceptually. However many people we had. So they're super different. I'm not worrying about formula now, guys. Don't worry about the formula. Is that what what's the difference?
It wouldn't be multiplying like people by common from a comedy action. 20 people was. It wouldn't be quite. It wouldn't be 6.
In the degrees of freedom? Are you talking about the numerator or the denominator? In the denominator, I'll do this now, but this isn't what I wanted. So if you have 20 people in each group, and remember, you're calculating 3 different sums of squares. So just in this group here, how many pieces of information do you have? How many pieces of information do you have? 20. You have 20 scores. So you have 20 scores here. And then how many things are you estimating? 1 group mean here. So how many can vary just in this one distribution? 19. Now let's go to the next one. You have 20 people in this group. You're estimating, so you have 20 pieces of information, 20 scores. You're estimating 1 group mean. You've got 19 that can vary here. And then same, 19 that can vary here. Your degrees of freedom is 19 plus 19 plus 19. Does that clarify? But if you ever have a degrees of freedom error that is small, 4 or 3, you should be going, alert, alert, that can't be, because it's always going to be based on how off individual observations are. And you're never going to have 5 people in your study. So that should be a signal for you of that can't be accurate. Variables do you have? Is the variable design between or within person? So is the study design a between groups design or within groups design? And then how many levels of that variable do you have? So let's do it. Is there an effective environment, alone, peer, group, on performance? Is the variable measured between or within? We could also test this exact same question with a repeated measures design or a within person design. In this case, we'd put the same people through each condition. Do a task by yourself, do a task with one other person in the room, do a task with a group in the room. In this case, the participant would experience all the conditions. And if we're being really specific, the question is a little bit different. We really want to know, was there a change in performance? Or was there a difference in performance based on what condition the person was in? I like keeping that word change because it keeps us rooted in the same people. So notice, you cannot identify a test by the research question alone. You have to have all 3 of these questions, and you can't get these 2 until design. Really do research. No one asks a research question and then says, I'm gonna do an ANOVA. They say, I got a research question and then I'm gonna design a study. And then I'm gonna do an ANOVA. So design comes first, then test ID. So what are we gonna do here? Dependency test. Not an ANOVA. We don't need to do an ANOVA. There's 2 levels. Questions about that at all? You're gonna do the next one, but I want you to do these 3 things. Draw the model, identify the design, and then the test. Go. Go. go, go. Kind of achieve, because you don't really need to draw the model, because it's really obvious. Which means I'm never gonna put one of this on the exam. What's the number one mistake that people make in test identification? I'm in a ANOVA class, so it needs to be an ANOVA. That's why I gave you that t-test example. Because out in the world, you're not, oh, I'm in an ANOVA period of my life, so I need to only run ANOVAs. You have to be able to take all the analyses that you've learned. There's a reason we go through that model building process on day 2 of this whole year, and why I write that huge guide on it. That's the logical thinking process you should be following. So step 1, ask the research question. Why? Because that is what allows you to draw the model. How does room composition affect the cognitive performance of Black high school students? Then what are you gonna do? Then you're gonna draw the model. Room composition, Black, white mixed, between subject design. Notice we're not at statistical model yet. Once in each room, what's the design? Within subject design. Study, go collect your data. And then after you collect your data, what are you gonna do? So collect and prepare. Then what do we do statistically? Thank you. Specify your model. You're gonna specify your statistical model. This plus your design is going to inform what tests we run. So guess what? The model for these two is the same within group variance or within subject variance. All Black room, all white room, and mixed room. They're gonna have a score here, and a score here. Then participant B is also gonna go to the all Black room, the white room, and the mixed room. Now, what did I do? Do I have any idea what is represented in here? Which room? All of them. I averaged all the rooms. So it has nothing to do with room. I just averaged them. But what it is telling me is just holistically, what's the difference between participant A and participant B? Those are stable subject differences, and they are between person, because they're the differences between participant A and participant B. Because we only have, how many measurements do we have for each person? One. An ANOVA is a one-way ANOVA, 2. So I should be able to find something in the flowchart and highlight it in the circle, and vice versa. So how do we partition one-way ANOVA? We have all of our variance. It's easy. It's either variance that's explained by our model or variance that's not explained by our model. How many sums of squares values do you get in your output for an RM ANOVA? You get all 3. You get this one, you get this one, and you get this one. You get the final partitioned sources. But these two are grouped together as within sources. Those two. So if you look at your output of an RM ANOVA, you have the between source, but it doesn't have anything under the F means all that stuff. That's also why we do it this way. Because this ratio of the 2 different types of within subject variance are what makes your F step. So if we take total variance in the data, we have variance that's explained by our model and variance that is not explained by our model. And in our model, we have how many things? 2, our treatment and our covariate. Then if we break that model into its 2 pieces, we get our actual treatment, our actual predictor of interest, and our covariate. That's the really simplistic one. The focus of the ANOVA lecture was that ANOVA makes 2 adjustments. So here's another way of thinking about how ANOVA works. But instead of regular kind of all sums of squares model and sums of squares error, it starts with an adjusted sums of squares that doesn't include your covariate, and then splits it into adjusted sums of squares of your model and adjusted sums of squares of your error. So it actually starts by kind of removing that covariate to begin with, so that the impact is not just a reduction in error, but also an enhancement or adjustment to the how do the means vary around the grand mean part. There's no yes, no, really for any of these. So somebody asked, wait, sometimes the histogram of the residuals look skewed, or my histograms look skewed. but the skew and kurtosis were fine. That's because we should never trust anything directly with our eyes. The scaling of the graph can change what it looks like. The number of the way they make the bins in the graph can change what it looks like. And then again, there's no such thing as skewed or not skewed. There's degree of skew. And what you're saying is it looks the degree of skew is too high. And then the measure of skew is telling you, well, how high is it really? And then we can also do more sophisticated things, like transformations of our data, which we won't get into yet, or actually, you know what? Our data is not even close to normally distributed. I cannot run a test of means. What is the definition? That the variances of either the outcome in each group or the differences between each condition are not significantly different from one another. That definition is identical to the null hypothesis of the test that we use to test it. That is the null hypothesis for each of those. Why do we care, ANOVA? We pool them. Remember, we have the sums of squares for A, the sums of squares for B, the sums of squares for C. We put them all together and that's our sums of squares error. But the concept is, I think, more easily explained with this idea of anytime you're averaging things that are wildly different, you're going to get something that is not representative of either of those. Here, we're just averaging variances. How do we test it? Homogeneity of variance, we test it with Levine's. Sphericity, we test it with Mockley's. You're gonna have to come up with your own way to remember that. That is, you have to memorize. You just, Mockley's is always gonna give us a correction for degrees of freedom. It's gonna give us an epsilon for correcting degrees of freedom. If we violate sphericity, we can still report our ANOVA. We're just gonna report it with adjusted degrees of freedom. What does adjusting degrees of freedom do? First of all, when we adjust the degrees of freedom, this is the difference between procedural understanding and conceptual understanding. When we adjust the degrees of freedom, do we adjust them up or down? We're only going to return a significant result if you really have differences. How much so? Well, it depends on how much you violated it. If you violated it a lot, we're going to push your critical value all the way out. Congratulations, luck. If you violated it a little, we're just going to move it a little. That's what we're doing. We do sphericity. How do you report it? A Levine's test confirmed the data did not violate the homogeneity of variance assumption. Remember, anytime you make a conclusion based on stats, you got to report the stats. Mockley's test indicated that the assumption of sphericity was violated. It's fine for you to just say W. You don't need to give the chi-square. Someone was, what does the number after the chi-square represent? That is the Mockley's W. That's the test statistic for this test. I'm not making you do the W by hand under the hood. W equals 0.44, P equals 0.002. Therefore, degrees of freedom were corrected using the Greenhouse-Geyser estimate of sphericity, and then tell us what that correction estimate. We need to report what? The W and the P value. If it's not violated, the rest of it is not needed because you're not correcting anything. You're just using the standard ANOVA results. Needs to be linear. Remember, all participants are Black students. What do we expect performance will do?
It'll go up.
No?
It'll go down. I mean,
It'll go down.
opposite.
Probably not. There are probably other things that factor, so it's probably not crazy. But it's this. That's a linear relationship, meaning if I draw the line that fits the data, it actually is line-like. If my data looks this, guess what the general linear model is still doing? Fitting the best line it can. And the problem is that's not necessarily bad. In fact, we love finding interactions. But does ANOVA tell you anything about an interaction? No. So guess what happens to that interaction? Stays hidden. You don't see it. So if we violate it, it gives us a hint, hey, we need to run something that will allow us to check if there's an interaction going on here or not. Otherwise, we're ignoring that can exist. Now, we know we have 4 groups. The other thing I really like drawing for sums of squares tables are the mean, a representation of the means table. So we have 4 levels of our predictor, which means our degrees of freedom is 3. The prompt only tells you the same number in each group. So how am I going to figure out my degrees of freedom? This group of 20 people, how many degrees of freedom for just this condition do we have? 19. So 19, 19, 19, 19. Very simple partitioning of variance. Total is either model or error. So if we have model and we have error, squares. So if you're trying, rather than just be like, I gotta use sums of squares for eta, you can think conceptually, effect size is agnostic of sample size. So I can't use mean squares because that involves sample size. So if we take 1995 and divide it by the total, how much variance can be explained by our treatment relative to all of the sources of variance versus, that's eta, versus how much variance can be explained by treatment compared to unexplainable variance or error variance. That's partial eta. So visually, what it looks is this. It is in an ANOVA. That would give us the sums of squares compared to the whole pie. But we don't want to know that. We want to know sums of squares of our treatment, of our predictor, relative to our error. So we usually ask for partial eta, again, in an ANOVA. The important conceptual piece to understand is that which of these will always be bigger? Any other systematic sources of variance. That's the key. Those wedges that don't get counted in partial eta, those are the other systematic parts that are unique to that type of ANOVA. I don't know where, and directionality is this is higher than this or lower than this. So no, we don't get directionality from the ANOVA. We only get directionality from the post hoc testing. The most important thing that we need to understand about post hoc testing is why we do it, which is that we don't run a bunch of t-tests, because if we ran a bunch of t-tests, every time that we ran a t-test, we would drive up our overall probability of getting at least one type 1 error. What is that overall probability called? Family-wise error rate. The idea that we're never, if we're doing post hocs, we're never doing one t-test. We're always doing multiple t-tests. If we just run them as regular t-tests with a 0.05 alpha, we are with every t-test we run, we become more and more to make at least one type 1 error. So instead, we're going to correct our individual alphas for each of those t-tests using one of the 2 corrections, either Tukey or Holmes, which is kind of the middle of the road correction, or Bonferroni, which is a lot more stringent. I'm fine. So here's the issue. The only way to decide which one to use is completely contextual. We're going to use Bonferroni if your specific research study cannot have a type 1 error. Sometimes it's worse to make a type 2 error, and in some research, it's worse to make a type 1 error. So I can't say here, so that's why I say in here, we can always use the moderate middle of the road. Because you as a researcher would need to be able to say, I know that in my study, type 1 is not. For the most part though, Holmes and Tukeys are fine. Cool. All right. So literally you should be able to say, that's taking the mean of black, the mean of white, the mean of mixed, subtracting it from the grand mean, and squaring all those and adding it together. If you don't explaining it, just draw it. That's grand mean, and then here's black, here's mixed, and here's white. That. Then we divide it by our degrees of freedom. We get our mean squares. What is this? Variance. Variance. It's how each of those group means vary around the grand mean. Now we can go to our residuals. sum of squares, each person's individual score, how far away they are from their group mean, squared, added together, divided by degrees of freedom, and this is our error variance. That ratio is our F. Our p-value is the probability of getting that F or something more extreme, assuming there is no difference in performance based on who you're in a room with. See, you can never escape A. And our eta is 0.09. How do we interpret that? 9%. Be careful, specificity, it's gonna kill you on Tuesday. 9% of the variance in performance can be explained by room condition, that's fine. Cool. Then, so we know there's a difference, we don't know where. So we have significance, we don't have direction yet. We do have overall magnitude. Then we can do our pairwise comparisons. Students in a black room versus students in a mixed room. There's a 0.15 difference in our sample data in performance. And using our means here, we can see, well, which one was higher between black and mixed? What? 84.25, 84.10. What's that difference? 0.15. It's our mean difference. I don't see surprise faces. That scares me. That is our mean difference, is the difference between means. I still love you, but that scares me. Now, is that a really big difference? No. In fact, that difference is not significant. That difference is not significant. Now, in our sample, there's a mathematical difference of 0.15. There will always be a mathematical difference in your sample. The significance part is telling us, should we blow up that difference to the population and assume that that always exists? No. So if our p-value is not significant, then out there in the world, there's no difference in performance based on whether you're taking a test with all black students or in a mixed room, even if you see a numerical difference in your sample. So now let's look at an all black room versus an all white room. Is there a difference? In our sample, our descriptive stat, 18.81. Yes, it's significant. So we can infer that if we collected every black student and we did this, that we would see a significant difference between being in a room with all black students and all white students. And then, is there a difference between mixed and white? Yes. Our standard errors are always going to be similar or identical, depends sometimes mathematically, but that has to do with the pooling. We're pooling that error. And then we have our effect size. We can use D here because it's a measure of a distance between two things. How far apart? And it's literally saying, let's take mixed versus white. Mixed is 84.10. White is 65.44. That D is saying these two numbers are 0.66 standard deviations away from each other. That's what that D is telling us. Relatively straightforward in ANOVA. Now, this question of how do I storytell? I think the easiest way to storytell is to go from this, which has a lot of information. You don't need all of these numbers to tell a story. You need a lot of them, but you don't need all of them. You need all of them for different reasons. Why did this happen? How big is the difference? But you don't need all of them for a high-level story. What you need for a high-level story is to know is there a difference and where is it? That's it. So take your means and use your results to annotate your means we've been doing in class, or your graphs if you have a graph. So was there a difference between black and white? Black and white? Yes. So I'm going to say yes, that is different. When I say that is different, what do I mean? Obviously 65 and 84 are not the same number, but that's not what I'm saying when I say they're different. Emily? In the population. These numbers are what? Descriptive. These numbers are what?
happening in us.
Descriptive. That's just what happened in my data. It's the inference part. It's the fact that we're doing null hypothesis significance testing that allows us to either infer to the population or not. So this is descriptive. When I put a check mark, what I'm saying is this is a statistically significant relationship, meaning we can assume it holds or conclude it holds in the population as a phenomenon. How about white versus mixed? Yes. How about black versus mixed? It was no. No. Stop. This is how you tell the story. Now, the number one issue that people have with this and the storytelling is they tell a piece of the story. So they'll be like, hey, students do better when they're in a room that has all black students than they do when they're in a room that has all white students. Or even more than that, a more missing headline here would be students do way worse when they're in a room full of white students. Black students do perform worse on a cognitive task when they're in a room of all white students. That is factually accurate, but it's missing something. What is it missing? Better. It's that there's no difference in performance as long as the room between when the room is all black students and when the room is mixed. So now think big picture. If I want black students to do well from a performance perspective, do I have one option or two options? Two. I have two. My research would suggest that either of those will help them perform better than if I put them in a room with all white students, but it doesn't matter if I put them in a room that's all black students or in a room that's mixed. So my number one advice for the storytelling part is simplify it down, either with the graph or the table, and then make sure you don't forget a piece of the story. If you wanted to, you could go line symbol by symbol and then see if you can condense that more.
That's exactly what I was gonna.
Sure. If you want to be, because that's kind of what we did. We said there's a difference in performance when students are in, and we could even say better. Students do better when they're in a room with all black students than when they're with white students. And students do better when they're in a mixed room compared to when they're with all white students. But there's no difference between whether they're with mixed students or black students. That's technically correct. It's just kind of muddled. It's just wordy, but it's not wrong and it's not missing anything. So if you're nervous, sure, go piecemeal. That's fine for now. What that means though is that you haven't solidified the story in your head. If you have to go piecemeal, you haven't gotten to a point where you can walk down the street and someone, what did you find? So take a second for that synthesis step. I was like, do I write a full APA write-up or not? No, we've done it. There's a ton and it's in the interpretation guide. And that's not actually going to help you because the problem is that every write-up is going to look slightly different depending on what results you got. So instead of giving you an example, let's make a list of the things that need to go in it. So what's the first thing that needs to go in it? And we're going to make it together. I'm not going to tell you. Means are not the first thing I'm going to share. No, what? Not even. So type of test. There you go. Say it again, Heather.
Type of test used to address.
Type of test used to address some research question. I ran a one-way ANOVA between groups one-way ANOVA to determine whether there's a difference in blank based on blank. Then what's next?
Checking assumptions.
Prior to analysis is usually a word I use all the time. ... I checked assumptions. Assumption 1, whatever it is, violated or not with statistical evidence. Repeat with assumption 2. Repeat with assumption 3. Cool. Then what? Test. For us to analysis, you do not need to use my words. I'm just giving you narrative transitions. Proceeding to analysis, we found or did not find a main effect of IV on DV. Now, what stats? F, what else? P,
Confidence interval,
don't get it, you can't get it. What?
eta squared.
Eta. Or partial eta. Then what do? We have significance, but we also have what here? This was, you don't even have to say big or small. I don't really care, honestly. I just care that you understand, oops, how to interpret it. Blank percent of the variance in can be explained by, you guys know you've done this 4 times. Just making sure. Sometimes I think you're, but you actually don't, just, you know how to do this. You do. So, proceeding finalis, we found out, did not find. If, let's assume we did for a second. If we didn't, what would you say next? If we did, we then did what? Post hoc pairwise comparisons using something, either Tukey or Holmes. So we did a post pairwise, and then there was, now here's where it gets really hard for me to give you a way to do it. Because if they're all different, you might just opt to say, you might narrate it a different way. Or if you might say, let's take the example we just did. Students in a room with all Black students, participants in a room with all Black students did better than with white students, but not with mixed students. You could organize the pairwise comparisons in whatever way. But let's at least be clear of what needs to go into those pairwise comparisons. So we're going to report pairwise comparisons. It's if you report them one by one, if you don't feel comfortable integrating yet. And what are we always going to report? Means and standard deviations for condition. So students who did the task in an all Black room, mean standard deviation. We get those from our descriptives. Did better than students who were in an all white room, mean standard deviation, mean difference, confidence interval, and effect size, which is what? Because it's a pairwise comparison. Mean, standard deviation, mean difference, p-value, confidence intervals, effect size. Am I missing anything? We're not there. Go ahead. I'm not reporting an ANOVA. I'm reporting a regular now. There's other specific stuff you're going to have to add depending on the flavor of ANOVA. This is basically whatever you did, you have to share. The number one rule of thumb for reporting is just don't leave a reader guessing. So if you controlled for something, you're going to need to say controlling for, and you're going to need to report the F for that also. So there's an effect of your covariate, which you're also going to report.
If you found no significant between in the post hoc, can you just say we found no pairwise differences? See table.
But the correct APA thing to report in that case is mean difference, not means. What p-value are you looking at to make decisions in an ANOVA? Well, let's draw the model. The model is room composition. Does room composition impact performance? So the p-value that I'm going to use to investigate whether my hypothesis was supported or not is the racial ID line is giving me, if I color code these, there's my relationship of interest. The racial ID line is giving me, so if this is my relationship of interest, and I say, yes, there is a relationship between room composition and performance. There's a relationship, actually in this case, there is not a relationship. There's no relationship between racial ID and performance. Then what am I going to run post hocs on? The thing I want to know, room comp. So my post hocs look very similar to my one-way post hocs, because they are, with one difference, which is look at my means are adjusted. So if I were to compare this result with my one-way result, my error here would be smaller than it is in my one-way, and my means would be different. There are your two adjustments. If we look at them next to each other, here's what they look not adjusted. Here's what they look adjusted. Now, this is another example where it's not a massive adjustment. So let's look at a different example where it's way more adjusted. So let's say we're interested in studying the effect of different types of resilience training on self-efficacy. So there's 3 types of training: cognitive reframing, stress inoculation, and mindfulness practices. And the researcher is going to include baseline anxiety as a covariate. So let's look at the means of self-efficacy if we ran a one-way ANOVA, unadjusted. What would you conclude? There is no difference in self-efficacy based on what type of resilience training people took. But now look at the results when we adjust for our covariate. Now what might you conclude? Well, at least you conclude mindfulness probably doesn't work. Maybe, potentially. Finally proved the other way. I'm still singing its praises. So how do we explain succinctly why those means are different? So here's another example of specificity. She said we need to control for we weren't controlling for people's baseline anxiety in the unadjusted means. Yes, but I want us to take that a step further. What was that doing? No, we're not dealing with the error component here. This is just the one adjustment to the means. It's treating everybody in the adjusted means as if what? As if they started with the same level of anxiety. And sometimes, depending on what you're studying, you can make other inferences basically about why something would or wouldn't have caused. Because in this case, we're controlling for baseline, but we could control for other types of covariates. And depending on what you control for, you may be able to tell more of a story about why you couldn't see it and now why you can. It depends on the context. The only thing I want to touch on in an RM ANOVA is that this partitioning of variance is different than the partitioning we've seen for ANOVA, one-way ANOVA and ANCOVA, in the sense that we first break it up by between and within, and you don't have any FP, ADA, etc. for our subject variance because that's just being parsed out, does not go into our F formula. That's what makes all things held equal. That's what makes an RM ANOVA have more power than a one-way ANOVA if you kept everything else the same. Now, where'd it go? Here we go. Check out the sphericity assumption here. I wanted us to see a concrete example of this. So sphericity, meaning are the variances of the different scores not significantly different from one another? Are they significantly different from one another? Yes. The sphericity assumption is violated. So what are we going to do? We're going to correct our degrees of freedom by this greenhouse geyser. Now, you have to be very careful because what does that mean you're going to report when you get here? This. And guess what? If you look at the epsilon, which is 0.64, so epsilon is 0.64, all we're doing is taking 2 times 0.64, that's what gives us 1.28, and 58 times 0.64, that's what gives us 37.18. It's literally that correction factor. Good. There are some fun questions for you to have fun with.